Hello everyone, my name is Cohen and I will present the work out of distribution detection without class labels. This is joint work with Ron Abutbul and Yedid Hoshen, and we are all from the Hebrew University. So we look to identify anomalies, and anomalies are any samples that differ from the normal train set in a meaningful way. For example, if our normal train set would have been only normal images of hazelnuts, so anomalies might appear as hazelnuts with some defect on them, or images of cats or flowers. And we assume that we do not get to see any anomalies during training, and this is very challenging because anomalies might appear in many ways, and it is hard to predict which kind of anomalies we might encounter during inference. So the setting is called one-class classification because we only get to see the normal class during training, and there are many applications to it, including in manufacturing, security, or science. For example, in scientific missions, it is often the case that the most interesting samples are the ones that we never saw before because they represent new phenomena. And we specifically look at multimodal anomaly detection in images. So our normal train set is composed of many classes, for example, the CIFAR10 classes, and we simulate anomalies as any image that comes from another dataset, such as CIFAR100, SVHN, or LSAN. And previous work comes both from one-class classification community and the out-of-distribution community. So from the one-class classification community, we have works such as CSI or SSD that use contrastive learning to learn their own representation of the data, their own feature embedding based only on the supplied normal data. And other works, such as Panda or min-shifted, rely on very large datasets, such as ImageNet, to learn strong pre-trained features, which are useful for many other visual tasks, and adapt these features to the specific dataset that we want to detect anomaly with respect to. Somewhat similarly, the out-of-distribution detection community also looks to detect never-seen-before samples, but they do assume labels on the normal data, so they can train a classifier on the normal data and use it to identify anomalies. For example, looking for low confidence in the prediction of class as indicating of never-seen-before sample. And most of the one-class classification method focused on unimodal datasets, where the normal trained data is composed of a single semantic class. There are some works, such as CSI and SSD, which did evaluate on multimodal datasets, and we compare to them in this work. So basically, the main goal that we aim to achieve here is to adapt a state-of-the-art anomaly detection method such as Panda or min-shifted to work with a multimodal train set, a normal train set that is composed of many semantic classes. Our key idea is to use pre-trained features and adapt them to better describe our normal data using deep clustering priors. This is somewhat similar to the well-known Gaussian mixture model method that takes the data and fit a set of Gaussian distributions to the data. But it is not quite the same. We want to adapt deep features and learn a deep representation of the data based on somewhat similar distributional assumptions. And this is in the spirit of the work Panda that is doing feature adaptation based on a unimodal distributional assumption. So the general framework is that we get very strong pre-trained features, for example, trained in a supervised manner on ImageNet, and used priors that describe multimodal data to adapt them to better describe the normal train set at hand that we want to detect anomalies with respect to. So in order to adapt our features using multimodal distributional assumption, we turn to the self-supervised clustering community and adapt scan, one of the well-established self-supervised clustering methods. Scan starts with a representation learning stage. It uses CMCLR contrastive learning in order to learn a feature descriptor of the trained data, and then it retrieves for each image the k nearest images from the trained data, as we can see in the illustration. Next, it learns a classifier that should split the trained data to the different classes, and it uses three kinds of losses. They use an entropy loss in order to encourage an equal number of samples to belong to each class. They use sample-wise confidence. They want each sample to be confidently assigned to the class that it is assigned to, and they want nearest neighbors that were calculated in the first stage to be assigned to the same semantic class. And they finish with some self-labeling procedure. And the first thing that we found that was quite surprising is that using the scanned features on their own already gives very strong results, even state-of-the-art result, or on par on some datasets. So we just took the features from the last stage of the scan method, and we used KNN scoring or density estimation. So we took the entire normal train set, for example, CIFAR10 images, and mapped each image to a vector representing it. And during inference, we took each test sample, we mapped it to a vector, and we gave it an anomaly score according to the k nearest distance between the vector of the test sample and the k nearest train samples in the embedding space. And we expect that anomalies would be found in less dense, in areas of embedding space of lower density, as they represent some semantic properties that we never saw before. But now we want to do even better. We want to use transfer learning from a large network pre-trained, for example, on ImageNet. And we want to take this representation and in some manner make the normal data more dense with respect to the anomalies that we do not get to see during training. But we will want to use, again, density estimation based on nearest neighbor criterion. So we want to make sure that each of the normal samples would be found relatively close to the normal sample that we saw during training. So now we want to take our pre-trained features and use the adaptation of the scan method, their loss, in order to adapt the pre-trained features to describe our multimodal train set. So one approach to do it is to use scan, but in the first method, instead of using purely self-supervised features, to insert our pre-trained features. But there is some problem to it, which we can see in the table below. When we apply the second method of scan, the classifier learning, actually the ability of our feature to describe our normal train set and to differentiate between normal test sample anomalies deteriorate. And we say this is a special case of a catastrophic forgetting. So learning this new task of classifying the normal train set into semantic classes in an unsupervised manner makes our feature forget some of the knowledge they accumulate during pre-training, specifically their ability to distinguish between the normal train data and anomalies. We can see that later during the self-labeling stage, the feature regains some expressivity with respect to the anomaly detection task, but we want to do better. We want to avoid this catastrophic collapse phenomena. We turn to another approach which is based on two stages. So in the first stage, we use a self-supervised clustering method such as scan in order to get some approximate labels for the dataset. Methods such as scan do not exactly recover the ground truth classes behind the normal train set, but usually they give like very strong results. So maybe they give ground truth labels up to permutation to most of the dataset. And we want to use these labels, we refer to them as pseudo labels, in order to fine-tune our network, our strong pre-trained network. So in the example below, we can see that we have an anomaly, such as a white bear, and we look for the nearest neighbors in the normal train set between this bear and the images that we got during training. So without any adaptation, the bear finds some images that are maybe similar in color as the nearest neighbor retrieval, but we would like that after fine-tuning, it would not focus on features such as color, but maybe features such as the semantic class of the object, if this is the clustering of the normal train set. And we can see that after fine-tuning, indeed the nearest neighbor of the bear are only dogs. So of course, this bear is not a dog, and we do not want it to be a dog. It is an anomaly, and we are happy that the images that are retrieved for it are not very similar, but we can see that all the retrieved images belong to the same semantic class. And this is because our adaptation makes the pre-trained network describe all of the images that belong to this single semantic class with vectors that are very dense and very near to one another. Yet, our adaptation was based on approximate labels, pseudo labels that we achieved from scan. So we might want to be careful in scoring our anomalies, and this is why we use the k-nearest neighbors scoring. Melanobis scoring, for example, try to fit each semantic class with a Gaussian, but in this case, a few mislabeled samples for, let's say, a few airplanes that might by mistake have been given the same semantic label as a dog can really distort our Gaussian fit. So this is also some motivation for why we use the k-nearest neighbor scoring. And we can see that taking pre-trained features and adapting them with the pseudo labels that we got from scan gives us very strong results. So even comparing ResNet 152 architecture, we can see that we mostly outperform a previous method that uses similar architectures. And same goes in many cases with ResNet 18. Yet we do report results with the VIT architecture as well. And this is because we believe using this very strong architecture is actually a special feature of our method. Our two-stage adaptation methods allow us to take a very strong pre-trained network and quite easily adapt it to our normal train set based on the pseudo labels, somewhat in a similar manner to how some out-of-distribution methods work. Just not based on ground truth labels, but based on approximate ones. And we believe that we can do it without any special parameter tuning. We use the similar parameters in all the adaptations above. We have many discussion points in the paper, but one discussion point that I want to pay special attention to is the sensitivity of our method to the number of clusters. So self-supervised clustering have many hyperparameters, but knowing in advance the number of clusters is some prior knowledge on the dataset that we generally do not assume if we want to assume that our normal train set is unlabeled. So we did some experiments and we saw that in different datasets we can use more or less clusters and still get very strong results. But of course, if we use significantly too many or too few classes, or k, like estimate the number of classes, the result wouldn't be as good as we get with ground truth number of classes or something similar to it. We do want to mention DPM, a recently published method, which shows very nice results in automatically retrieving the ground truth number of classes for unsupervised clustering. Our method also has a few limitations I would like to discuss. So first, highly unbalanced classes. Following self-supervised clustering algorithm such as scan, we aim to split our normal train set into classes of roughly equal size. But in practice, we may encounter different datasets where one class might be significantly larger than another. To adapt our approach to this kind of settings, we might need some delicate care, and we do not address it in the scope of this work. Another limitation is non-standard datasets. We addressed mostly object-centric datasets, datasets in which the class, including whether we treat a sample as an anomaly or as a normal sample, is determined by a single coarse-grained object usually found in the center of the image. Yet, other datasets might be more focused on other attributes, such as coarse-grained features, as we can see in the illustration of the leaves, or maybe we would like to focus on the activity presented in an image rather than the objects. Addressing such challenges is beyond the scope of this work, and here I would like to mention that is not only this work, but I believe that the community in general, all of the current anomaly detection methods for images, at least the ones that I am aware of, kind of focus on these kind of visually salient attributes, and addressing these kind of more challenging data sets is something that I hope we will see more of in the coming years. Lastly, we rely very strongly on pre-trained features, and we know that pre-trained features work well for a large variety of datasets, even including some images that do not even come from optical cameras, but maybe X-ray or microscope images. Yet, on some specific datasets, self-supervised learning may outperform pre-trained features, and it is best, if possible, to use a combination of the two approaches, although in most cases, pre-trained features do outperform.